very much. Welcome back. So as I was saying, these black dots represent the parts of the subject that were important when it was started, and white dots represent what these fields have grown into. So essentially, I think everybody is interested in almost everything these days. But certainly algorithmic is quite common, and I want to emphasize the importance of feasibility. Don't necessarily try to make optimal solutions. Just like in pursuit evasion, I might not want to have the shortest possible path that the pursuer must go. It's already quite interesting to have any solution that works. It's guaranteed to work. If you want optimality, you pay a very high price. Sometimes that price is not worth it. And sometimes the criterion that you optimize with respect to is not very good anyway, especially when there are complicated obstacles in these environments that we tend to have. Anyway, so after I wrote this book, I realized that there's three areas that were really hard to work on, really hard to write. Motion planning under differential constraints, feedback motion planning, and information spaces and sensing. I put some time into these two, but I put most of my time into the third one, which is what led to this class. Again, this part of the talk is almost like a prequel. I'm telling you what motivated this course beforehand. Well, I'll say a little bit about motion planning under differential constraints and a little bit about feedback motion planning. These actually are both getting a lot of interest in the community right now, especially feedback motion planning. I will also say that feedback motion planning is not really too different from the way people are doing reinforcement learning, or optimal control if you want. Reinforcement learning, again, looks very algorithmic, and people put in obstacles and robot models and so forth, and learn optimal policies. Very, very closely related to feedback motion planning. So it's become a very popular subject, but I'm still putting most of my efforts into the third one here, which is this class. So for motion planning with differential constraints, the problem looks like this. So maybe I'm driving a car. Have you ever noticed that it's difficult to move a car sideways? Right? You can do it by doing parallel parking maneuvers, right? You go forward and like this, right? You can do these kind of maneuvers when you try to park. So that's a differential constraint. So I'm going over these three parts here. So if you have motion planning with differential constraints, you have to look at the reachable set of where you can go when you integrate forward the control system. And so you don't have complete control. You cannot just simply move on a straight line. So that's a local constraint. Obstacles can be considered as a global constraint. There are certain places where you cannot be, but you also cannot even move in the directions that you want to. So that becomes a very difficult problem to consider in addition to obstacles. Also, when you have dynamics, you have momentum. So if I'm moving very fast with a mechanical system, like a car driving really fast, you may have noticed that you cannot stop immediately. Excuse me. So imagine I have an autonomous vehicle. It's moving very fast. If I have a robot moving fast in this room, at some point I'll be moving so fast that no matter what I do, the robot will hit the wall. So I call this region of inevitable collision, RIC. This is also a state space or phase space. I should say phase space here. You may know that from physics, differential equations. So in other words, if this is the configuration variable, or maybe I took the whole configuration space and just collapsed it to one dimension, then we have another dimension, which is the velocity of configuration. So now you're in this new thing called the phase space, and so anywhere in the obstacle region in the configuration space is also an obstacle region in the state space. But you also have this bad idea here, this bad region here, which is the region of inevitable collision. So if I get going really fast, these regions grow, and they tend to dominate the planning. Right? So I don't want to go too fast, but if I go too slowly, it takes too long to get somewhere. So you have this kind of difficulty also when having differential constraints. This is just trying to generate a path in the configuration space, or sorry, a path through the phase space. And that's done by applying inputs, like I steer my car, or I fire the thrusters on a spacecraft, and I decide how to move and avoid obstacles. One of the big problems that people study here is called the motion primitive problem, and that is, what are some good policies, controls that I can apply to the control system so that I can greatly reduce the complexity of the control system itself. You can consider this as a problem of sampling in an infinite dimensional space of controls. There's all kinds of different ways I can turn the steering wheel over time. which ones are the right ways to do it so that when I compose them, I get a good reachable set. For example, Emilio Frizzoli made a nice thing. He made this thing called a maneuver automaton, which was for helicopter flight. You can hover, which is stay in one place. You can move forward, or you can do a steady left turn or a steady right turn. So by switching between these, he made a very nice planning algorithm using RRTs a long time ago, around the year 2000. Got it to fly around through obstacle fields with moving obstacles in real time. Very nice because he very cleverly designed these motion primitives. So that's the third thing that people need to take into account for these. So there's been a lot of research on these. Back in the day, as I said, when we introduced RRTs, we made things like this, where we just added differential constraints to the RRT. Here's a car that drives and must turn smoothly, and this is a projection of a four-dimensional state space for that. So it drives very nicely and makes nice curves. So this is how it might look when you apply it to solve some problem of getting from one place to another. This one was kind of done for fun. Imagine you have a car that can only go forward and only turn left. Right? Your car is broken, you cannot turn the wheel to the right. You cannot even turn it straight, but you can turn it a little bit back and forth for left. And you cannot go in reverse. So imagine trying to get that car to go somewhere without hitting anything. Well, we put these obstacles in and we said we want the car to go from here to here, and this is what the method found, making an RRT like that. And we made one from the initial and one from the goal, and then we tried to connect them somewhere, and it decided to make this as the solution. That's pretty crazy, right?
The realistic situation is if the slots and the freezing wheels.
Yes. That's good. Oh, very nice. So you can only turn it some amount. Yeah, that's right. So if you use that security club for your car, you had better hope that the thieves do not get this algorithm, because they may use it to make a robot that drives the car and steals it, right? So very good. So that's all for planning under differential constraints. So are there any questions about that? That's a very big field of research. I could make an entire course about that if we wanted to talk about it for several days. But I just wanted to say that's one problem. I want to emphasize for you that getting from one place to another with no obstacles is not trivial. And there's whole research just on that, especially in the class called non-holonomic systems. Have you heard of that word? It's a very good term to look up if you've not heard of it. What that means is that the number of inputs or actions that you have to apply for your system is less than the degrees of freedom. So like a car can translate and rotate, so it has 3 degrees of freedom, right? When it moves slowly. But you can steer the wheel, that's 1 input degree of freedom, and you can step on the gas, let's say, to go forward, or reverse if you like, and that's another degree of freedom. So you only have 2 degrees of freedom on the input, but you have 3 degrees of freedom for the car. But yet you can get the car to go in any configuration, which is very interesting. So people care a lot about that. It usually involves differential geometry to study the structure of these kind of systems. This is usually something that computer scientists do not like, right? There's differential equations, but there's some beautiful math in here, right? You may find some interesting, there's actually some very interesting algebra, if you've ever heard of something called Lie algebras. It's a very interesting branch of mathematics. Lie algebra, so that's another interesting thing to look up. In fact, in this context, we have something called the control Lie algebra, which is a very special kind. Lie algebras come up classically in physics. Lie groups and Lie algebras are nicely coupled, and it's a subject I won't go into, but you may find that interesting. All right, another topic is feedback motion planning. So the problem next, aside from differential constraints, another independent problem is that we cannot predict where we're going to go in the future. We do not know with certainty exactly where the robot will go. There are imperfections. The wheels might slip on a rolling robot. If we have a vehicle that floats in the water, maybe there's drift in the current of the water, and we cannot predict that. A flying vehicle may be susceptible to wind, or maybe even the vehicles we make are not perfectly calibrated. Maybe I say go north, but I have a compass that's a couple of degrees off. So if I go north for 10 kilometers, I'm going to be very far away if I do not know the absolute true north with very high precision. So this happens all the time. We need to compute a feedback plan. Here I say X goes to U. The actions that you take U, we had actions before in this course. depend only on the state. So instead of parameterizing a nice path, I say, no, you need to say what to do from every state, because wherever you end up, you need to specify what action to take. Remember previously I made plans like this that used information feedback. But remember here we have perfect information. So if we have perfect information, that is equivalent to state feedback. I know the state all the time. I still have the problem of not being able to predict the future state. So that's what leads to feedback planning. And you may have a control system like this, or you may not. There's one parenthesis missing there. And during execution, a sample path is generated. So in other words, when you apply the algorithm, you will go somewhere, but some of it may be unpredictable. So if you apply the algorithm again, in the same circumstances, you may go somewhere else. And remember, powerful sensing is assumed here, so we should feel very guilty about that. But nevertheless, it's a very important area of research. If I just have a discrete grid, a feedback plan looks like this. Everywhere on the grid, I just tell you which direction to go. Therefore, if you have some unpredictability, if you land somewhere, it's clear which direction you should try to go. So that's the way a feedback plan looks to get to that goal right there. And then if you get there, you terminate. I put an action called a UT, which is the action that terminates. You're done. Here's something that may look like a computational geometry kind of feedback plan. I do the triangulation like I had before, but then for each triangle, I show which way to go. I point to which edge you should exit from. So it's very easy to compute a structure like this, and we could even move this around and then change the flow, right? By very simple computations so that we always flow to the goal. Even if the goal is moving, we may always point to it. If I look at the paths I will get by just following these directly, they will be piecewise linear. People don't like piecewise linear paths in control theory because you have to stop and turn. So if you have momentum, they would rather move in a smooth way. That motivated some research that we did, which it's coming up in just a bit, but before I do that, here's another way to look at it. People like to make something called a navigation function, or Lyapunov function, or potential function. They're all similar ideas. The idea is that you make a kind of function so that when you take the gradient, you arrive at the goal by gradient descent. The computations you do for that look a lot like continuous Dijkstra. You may have seen continuous Dijkstra algorithms. Hirschberger and Suri, if I'm not mistaken. Is it Hirschberger and Suri? Or no, it's somebody else. That's a different algorithm. I cannot remember. Who does the continuous Dijkstra? I cannot remember the best algorithm for that right now. I know Suri is one of the authors. Okay, it escapes me now. Yeah. Hirschberger and Suri may be one of the visibility algorithms.
Like fast marching.
Oh, it's also like that, but what's different from fast marching is that fast marching is based on numerical PDE, partial differential equation solutions. This is beautiful and combinatorial. So it is the same kind of thing, but this is done in a clean combinatorial way. And if you use fast marching for this kind of problem, it would be, let's say, foolish, because you can do it in a very exact, fast way. If you have a more complicated differential constraints or differential equations for your problem, then all you can do is something numerical like fast marching. So people make a function like that and then do gradient descent. But what I want to say is at the end of the day, you're supposed to compute a vector field over the space where you have a flow. So one thing we did along this with my student Steve Linden a few years ago is we partitioned the space into simple cells, and then we used a cell conductivity graph to determine some kind of high-level plan that flows to the goal discretely. And then we make local vector fields inside of the cells that flow in the direction of the plan. And then we get rid of discontinuities in the vector field itself by smoothly interpolating the fields. So to give an example of how that looks, we may have some arbitrary cell decomposition like this, and then we compute some kind of vector field over that flows to the goal smoothly from everywhere. The vector field itself cannot be smooth everywhere. You can see there's a divergence in the field there because there are topological obstructions. It's well known in topology that you cannot make a vector field on a topological space with holes like this that is smooth everywhere. However, the trajectories, the flow that you get if you follow a path is smooth to the goal. You can even apply this, and we did in our work, to that method of cylindrical algebraic decomposition. So even in the most 27-dimensional, highest dimensional kind of motion planning problems you can think of, except for infinite dimensional, but for the hardest of finite dimensional problems, we showed how even for cylindrical algebraic decomposition, you can put a smooth vector field over it with very low cost and no additional complexity. However, computing the decomposition is hard. So only if you have simple decompositions can you use our method, but once you, it's not our fault, it's just that the decompositions themselves have high complexity. There's no way around that, as I said, due to p-space hardness of motion planning. It's quite difficult to get around that. But if somebody gives you a decomposition, what we tell you is you can compute a smooth flow for free, or a smooth vector field for free. Yes, and yes?
Is it possible a local minimum occur in this situation?
Oh no, that's what I mean. We construct it in a very simple way over the cell decomposition. We first, discretely compute something like this, so that we compute the discrete flow. Very easy. You can do a breadth first search kind of calculation to do this, just like what was done in that two robot planning problem that Mansour talked about a few days ago. And then we make sure that if you enter this cell, you flow to this cell. If you're in that cell, you flow to this one. If you're in that cell, you flow away. So if you notice, all of the flows are directed here, so there's no local minimum problem. And in fact, we do not ever construct a potential function. We just directly make the field. So if you're taking the gradient of some arbitrary function that you've made, then you have a lot of problems. The point is that you can just directly piece together vector fields. Why not? Once you have a combinatorial representation of the space. Yes?
Does it work in dense environments?
What does dense mean?
It has lots of offsets.
Yes, no problem. Yeah. In any space where you can make a decomposition, you can apply this method very trivially by just defining constant vector fields and then smoothly blending them together with very simple interpolation formulas.
Does BFF and for all BFF?
Yeah.
I've used them and they haven't worked properly.
Which kind of methods? Which methods have you used?
BFH and BFF.
Yeah. Vector field histogram. Yeah, they may not. There's very often local minimum problems. This one thinks combinatorially and will work every time. No problem. It's a very new method. We did this in 2009, maybe, something like that. We published it.
Is this a 3D generalization?
No, let's go back to that again. So the generalization works in any dimension as long as you can get the cell decomposition. So it doesn't matter. So making the vector field is trivial once you have it. That's the news. Once you have a cell decomposition, the vector field is trivial. Your cell decomposition may be cylindrical algebraic, or it may be a simplicial complex. So you have a decomposition into convex polytopes. Either one is very easy. Maybe for some other decompositions, it also might not be hard, but we did not do it. Any dimension. But you have to get the decomposition. Yes?
Is it possible to apply this approach in unknown environment?
Sure, you can keep recalculating and updating this. As long as you can get cell decompositions efficiently for your problem, you can recompute a vector field, no problem. The main downside of this method is that the particular flows we get are sensitive to the decomposition. So if your decomposition has a lot of small cells, the flow may go like this. Like it may be like a staircase, but that's just an artifact of the cells. We've been trying to figure out ways to make it even smoother, but we don't know yet. So there's definitely room to improve this. I think people are not too aware of this. There's this idea from computational geometry called bump functions. So if you look that up, it's a tool that's used in differential geometry. I believe it's if you know some differential geometry, it's in the part of in most textbooks where they try to construct partitions of unity. It's called partitions of unity. And it's like trying to cover a space with smooth vector field patches. And it turns out that you can blend all the patches together by doing these things called bump functions. So it will smoothly blend together, a bunch of vector fields that themselves, each one is smooth, but they would be discontinuous if you just put them together. So you can very easily do interpolation to blend these together. You do not end up, however, with an analytic vector field. So if you know about analytic fields, analytic functions means that you can reconstruct the entire function from the Taylor series expansion. So you cannot do that, but nevertheless, you get smooth curves here. I think it should be very easy and usable if you can get a decomposition. If it's low enough dimensional, it's very easy and very fast. If it's 2 or 3 dimensions, very easy. If not, it's up to the computational geometers to produce better decompositions for us. It's not our problem. I'm just saying that vector fields are free. Very, very fast, very easy to compute. Simple breadth first search with very simple interpolation formulas, and bam, you have a smooth vector field. It's not as hard as people think, but the decomposition is still hard. Yes?
Should you focus on cells or specific shapes or?
Yeah, in this case,
Space composition.
that's right. Well, as I said, the particular flows you get from our method will depend on the shape of the cell. The method works and it produces a smooth vector field. If you, for example, make like a grid of cells, then you'll get a kind of staircase in the flow, which is unfortunate, right? So there's probably a design problem here, which is very similar to like the triangulation design problem. You know, people talk about good triangulations and bad triangulations. Probably any triangulation will work for a lot of methods, but sometimes people like to have what no acute triangles, for example. You know, it may be a good idea in certain triangulations. So I think the same kind of thing will be true here. We tend to find that it's good to have these, well, the closer these cells are to a disk in shape, the better, right? I think, you know, so it's good not to have long, thin ones and things like that. However, it's not something we've investigated too much. I think there's a lot of room for that to improve this method and look at how it behaves on different types of decomposition. Any others? So again, any dimension is fine here. It's just, if you want to read more about this, you can look at this in the International Journal of Robotics Research, called IJR 2009. We have a full paper on that. Right. Other questions on that? So that's some example from our research. I actually think this is very different from how control theorists think. Control theorists think in terms of Lyapunov functions. And again, that goes back to when I talked about the different fields. In control, they want to construct a function that you can write down on paper. This construction is very weird to them because it's based on some kind of decomposition that is like the computational geometry way of thinking. But it's a perfectly valid vector field. So it's a very strange kind of thing, but something you thought was hard might actually be very easy. So we can talk more about that afterwards if you want. Maybe after lunch or tomorrow, as you like. All right. Any more questions? Yes?
Do you need a special grid to locate the origin of the vectors?
Special what?
Grid. Do you define?
Any decomposition is fine as long as the cells are two kinds, cylindrical algebraic ones.
I mean, inside the cell, you just graduate, huh?
Yeah.
The whole.
Yeah. If you want to apply this, then you need to do point location, right? Point location query, so that you know which cell you're in, and then you use the coordinates, and then you use whatever the vector is that you look up, and it will tell you where to go. And as you execute the algorithm, you can start from anywhere, and it will produce, by integrating this represented field, it will produce the trajectory. You don't need anything else. Yeah. Anyone else? Yeah, I really like this a lot. It really, it should work very nicely. I think people should take this into account. But it's inspired by both computational geometry and control. Very natural for robotics. It was surprising to us that it does not cost you anything more to make a vector field if you have cell decomposition. Like, for example, if you want to do motion planning for a ladder, as I said, like a line segment robot, it should be possible, not easy, but let's say possible, to make a smooth vector field over that space. You have to think about all the cases carefully, though. It's a bit tricky. All right. Well, after all of that I've talked about, the problem is that maybe it's expensive or impossible to accurately estimate the state at all times. Right? That's the message of this course, right? Don't try to estimate the full state. Everything I talked about for this part seems to do that, right? So remember what we talked about before. I'm going to start with a task like pursuit evasion or sweeping the floors or exploring. Start with the task and then design the sensors and filters. And then try to make the planning occur in the resulting information space. So in order to do that, we're back to this. This is the third of the 3 parts I was talking about. Planning with differential constraints, feedback planning, and then information spaces and sensing. So we need to develop sensor models, information spaces, models of complexity and computation over information spaces. Maybe we can eventually get to sampling-based planning and combinatorial planning in information spaces. The pursuit evasion algorithms, a visibility-based pursuit evasion, is an example of combinatorial planning over an information space. Maybe there are sampling-based methods over information spaces. Someone asked about particle filtering and SLAM and these kind of things. That would be an example of sampling-based planning over an information space that is a space of probability distributions of possible robot locations and maps of the environment. I would like to see these spaces get smaller based on the task. So I would like to see more of these kind of planning methods that we saw in this part, but applied to information spaces. That would be amazing to me, to see more and more of that. All right. So, for these information spaces, all these steps, they're not done, right? But for configuration spaces, to a large extent, we already had a lot of the mathematical machinery because the idea goes back to Lagrangian mechanics, which is quite old. Modern differential geometry got developed out of inspiration from physics, from Lagrangian mechanics. But, who's going to develop information spaces for us? Well, not the physicists. So, in some sense, I feel like we have to develop these spaces and understand their structures and then do planning on them. Right? Questions about that? That's the end of this part. See, I said this part was a little bit shorter. I'm sorry, some of you I know probably wanted me to talk a lot more about rapidly exploring random trees and a lot of these planning things and that. But, I'm sorry for that, but I can only talk about so much. And, I did that work a long time ago, too, so I want to talk more about current things. All right, let's see. And it also turns out that the people who are using RRTs these days and expanding them and using them in many cases probably have better ideas of how to use them than me, right? So I just did that a long time ago to introduce the method, but there are better experts than me on RRTs these days, I think. All right, so the next part, this is the last of the major parts, which is good because I'm running out of course time. So instead of planning directly over a state space or configuration space, I think we should be planning in the information space. So I have some slides on planning in information spaces. So first I want to give an information space view of planning, starting with the temporal filters. You remember the temporal filtering, right? The shadow information spaces was an example of that. The gap navigation trees was an example of that. So we have these temporal filters. Then I will talk about general planning kinds of issues, and then I will end with a bunch of examples. I guess there's a 10 here. It needs to be recompiled one more time. There's also the we're finally finished with something called the controlling wild bodies. Some of you might have seen. But so those are the different examples I will have, and then I have one final part after this, which ends the course, just some ideas for future research and such. So from filtering to planning. Well, let's take any information space like I talked about. This is how a filter looked, if you remember. You have a previous information state, a previous action, and a new sensor observation, and you need to figure out the new information state. Well, here's one way to formulate planning. I could say, why don't I pick a goal region in terms of information, right? So what information states constitute solution? For the pursuit evasion problem with visibility, that would be when you have a label of 0 on every one of the shadow components, right? If you arrive in that information state, you're done. It's beautiful because it does not express the task in terms of capturing the invader. It expresses it in terms of an information state. So the goal region, G, for pursuit evasion would be any information state where every shadow is cleared. You know there's nobody hiding, right? So we're very accustomed to that. So that's what was going on for that. I want to figure out, starting from some initial information state, what sequence of actions lead to the desired future information state. It's in the goal. Does that make sense? So that's all. So now I have the filter, but I want to force something interesting to happen. I want to get to some place in the information space. I need to design my information space so that I can detect when I'm there at the right place. If my information space is too trivial, I may be able to arrive somewhere, but maybe it does not correspond to solving the problem in the physical world. So we have to be careful with that. We still have this problem that the future may be unpredictable. right? So just like I said for feedback planning, maybe you cannot predict the future. So we have to introduce a plan that depends on the information state. I think I showed this a couple of days ago. That's the idea. If I have a plan, then look what it does to the filter. So remember the filter, the general filter back here, looks like this. The U is chosen by the plan. So if I apply the plan inside of a filter, then the filter looks like this, right? Oh, I guess I swapped the U and the YK. Sorry about that, but you can see that they're swapped from the previous slide. It doesn't matter in the ordering, but this one went U and Y. This one goes Y and U. Except the U here now is obtained from that function. Is that okay? Does that make sense? Right? So that, and how do I obtain that? Well, that function depends on information. It's just the I here. So this expression now no longer has a U in it, correct? You don't need U. All you need is the plan and the information state and the new sensor observation. So that's how it looks when you're executing a plan using these filters we've designed. And then I think of the information space I that's used here as just a new kind of configuration space. Right? It's the replacement of the configuration space. It's where you live. It's where you live, let's say, right? We're not really living there, but it's where I would say you live, so to speak, by having a sensor, and you can't measure exactly where you are. You cannot measure the true state. So you have sensors, or a sensor. It gives you information. You live in that information space. And that's what's actually being explored during execution. Questions? All right. So let's look at some general issues, and then I will give you a bunch of examples. And I think the examples, they help illustrate the idea, but I think they're nowhere near what is possible. So I want to leave you at the end of this course with the impression that I give you whatever few examples we came up with, but you should be able to find hundreds more. It's very, very interesting possibilities of applying these in future research, I think. All right, here's some issues that come up a lot in planning. So these arise repeatedly in planning. Predictability. Is the system predictable or not? Reachability. Can I get there? Can we arrive at the information state or state that we want to? People always ask about optimality. Do I have a good solution? And finally, computability. So is it even what I'm talking about here computable, even if there is a solution? We have to deal with efficiency of computation. So I'm going to cover each of these four. So for predictability, if I apply an action from an information state, can I predict what the next information state is going to be? In general, no. But if yes, then it's very interesting. I get a path through the information space. And that's a very weird and counterintuitive thing. Like, for example, here's two problems. The problem Frank talked about, sensorless manipulation. If I squeeze that part, I can predict exactly what happens. Even though I do not know the initial information state, I have no sensors during execution. So there's no way I can tell the difference. There's nothing that happens to me that's unpredictable while I'm squeezing this part. Strange, right? So that's why the solution in that case is a sequence of graphs. It's just a sequence. You do not need any kind of extra feedback. Very weird. So in the information space, I can predict exactly what's going to happen. Even though when we watch the movie, every time the execution depends on how the part was oriented. So if I did not know the initial orientation of the part, I could not predict what the movie is going to look like, right? However, in terms of the information space, I can predict exactly what happens. Same for pursuit evasion. You might have noticed that for visibility-based pursuit evasion, you give a path that the pursuer must follow, right? There's no surprises unless you see the evader, then the game is done. But let's suppose there is no evader and you're just trying to establish that there was never an evader, right? Right? It's like you've been given the task, like, oh, I heard there might be an intruder in the building. Run your pursuit evasion algorithm to make sure, right? If that happens, there's no surprises. Therefore, all you have is a path through the information space. All of those visibility-based pursuit evasion algorithms, the basic ones, are just constructing a path. Isn't that interesting? So sometimes it's predictable, and in these cases it looks just like planning. Maybe you can do combinatorial planning in the information space, which is what the pursuit evasion algorithms do. Maybe you can do sampling-based planning in the information space, if you have this kind of structure. If not, then you need feedback. You need information feedback. It becomes important, right? Just like those vector fields that flow, you need either discrete or continuous vector field that flows in the information space. That's what you need now if you do not have predictability. You don't know where you're going to go, so you need to specify the actions wherever you might end up. So that's what I'm saying. Just like feedback planning in the C space, you're now doing it in the I space, in the information space. Seem okay? Does that make sense? It's very interesting, right? So even in the centerless case, you have a path in the information space. This has a visibility sensor. It doesn't seem sensorless, but by the fact that you don't have to detect the evader, it becomes completely predictable. So it's very strange. All right, reachability. Sounds like there's an intense soccer match out there, a football match, right? More exciting than this. Maybe we can join in afterwards. Let's see. So reachability. So given a goal region, can I reach it from the initial information state? Is there even any way to get there, right? Do there exist actions that will take us there? Does there exist a plan that will take us there? If we have feedback, does there exist an information feedback plan that will take us there? Right? If there's unpredictability, we may ask, over all possible aspects of unpredictability, will I be guaranteed to get to the goal? Right? In spite of unpredictability. So that's another thing to ask, right? Another question, which is more basic, is whether or not the goal can even be adequately expressed in terms of the information states. And as I said, maybe I just have a trivial information space, and there's no way I can determine whether I'm solving the real problem. If I get there in the information space, does that really mean I get there, I achieve the task in the original physical world, right, or virtual world that I made from modeling? These are all very good questions. That's something we have to think about. Optimality. Maybe I have a bunch of plans that reach the goal. Some plans might be better than others. So, how should I decide which ones are better? What criteria do I need? Something to think about. If I do have a reasonable criterion, then I ask which plans are best or optimal with respect to the criterion. Just like you might know from optimization, sometimes an optimal solution might not exist, right? Does that make sense? You know this from optimization. Like if you optimize a function over a compact domain, then an optimum may exist. If you try to optimize it over an open set, then you might be able to get closer and closer to the optimum, but you can't actually get there, right? So you have to be careful of that subtlety sometimes. Does an optimum even exist? Does that make sense? Right? I'll give a very simple example of that. That's just very simple optimization. Got to be careful of when a solution exists. So if I want to optimize, I don't know, maybe this function over the interval 0, 1, but I only do it over this subset. It's an open set, right? You would like to get to linear function. You would like to get right here, right? That's where the optimum should be for this, right? But if it's an open set, you can't get there. Right? So just saying, does it even exist? Be careful of that. And computability. So given a description of the problem, can an algorithm be determined that automatically computes the plan? For some methods we have, the human computes the plan. A good graduate student will find the plan. And you can write an entire paper about it. That's fine. There's interesting things like that. I will show some examples of that coming later. Sometimes we want algorithms to find the plan automatically, like we did in path planning. Sometimes the plan is just a motion strategy that you cleverly design on paper. And that's also fine. Right? So it depends on the problem. As I said, here, like these things called bug algorithms, which I'll be able to talk about in a little while, next time. A clever human designs the plan. And then, of course, as computational geometers and algorithms people care about, what is the algorithmic complexity of computing a plan? How much time and space do I need to compute plans automatically? And then another thing that anybody who wants to do it with real robots or actually use the algorithms cares about is what is the implementation difficulty, right? Have you ever noticed if you've tried to use algorithms from computational geometry and other algorithms, as the complexity goes down, the complicatedness of the algorithm goes up, right? So that always causes confusion, right? People who want to use these algorithms in practice think, oh, it has low complexity, that's great, I'll use it. And then the computational geometry says, no, you don't want to use that. That was just a constructive proof, right, that the problem can be solved in this running time. That's all it is. Don't implement that, right? And so, so it's very interesting. There's always this kind of balance. You probably do not want to do the most naive thing. You may want to be clever and get the complexity down a lot, but you probably do not want to use the state-of-the-art, highly optimized algorithm in terms of complexity. So those are the four main kinds of things that that we tended to look at as in terms of planning. Let me go back to that. These are the four things I just covered: predictability, reachability, optimality, and computability, both theoretical complexity and practical kind of usability, let's say, of these methods. All right, questions about those? So that's how I view planning in terms of information spaces. Well, we can start off with, let's say, I don't know, maybe boring generic examples, just like we had these before for sensors and we had these for filters. Here's how planning looks in several contexts here. So I can have state feedback. In other words, in this case, the information space is X, and the plan is just state feedback. That's what I talked about in the last part, right? That's what the feedback planning looks like. It's a special case here. It's not another case, it's a special case. It's a case where the information space is designed so that your filters can always determine the state. I don't like that case very much, right? I'm not trying to encourage that one. That's what's normally done. I can do what's called open loop. In terms of discrete stages, it means you have a sequence of actions. Open loop is a term for control theory. If you don't know what that means or why it's called that, don't worry about it. It just means that you have a sequence of actions. The part of squeezing the parts is like that. You can squeeze this way, then this way, then this way. So you have a sequence of actions that you apply. That's the idea for that. This one's very nice. Pure sensor feedback. I showed you these different kinds of filters, right? You remember when we did filtering, I had these different cases? They correspond very closely to this. I showed you generic filters. Now they make generic planning methods. I can do sensor feedback. The plan in that case just says, based on the sensor observation Y, I tell what action to take. If your planning problem can be solved by pure sensor feedback, you should do it. It means it's memoryless, right? You don't have to remember anything else other than just a current observation from your sensors. If that works, then do it. It's great. Right? Hopefully you've designed an interesting problem where it's not so trivial that works. Maybe you can take a problem that somebody thought was really hard and then demonstrate that it's possible to solve with pure sensor feedback. Very nice if that happens. There's also history feedback, which is the most ridiculous case, which is take all of the observations that you have and all of the actions that you've applied before and make the action depend on that. This is the highest complexity sort of version here that you can get. Right? That's the biggest information space you can have. You can make your plan depend on that. So, as I said, recall that we have these filters over these information spaces that we've done before. And what we're doing with respect to filtering is we have now moved from being passive. Filtering is passive. You just gather in the observations and the actions, and you compute an information state. Now we're being active, which means that we choose the actions. Or we develop a plan that chooses the actions. The plan is pi here that chooses the actions. So that's being active, choosing the actions. All right, so here's the overall process. Based on the task, here's what I'm trying to do. I want to design a system, environment, bodies, sensors. We go back to the first part of the course. And after that, I think about it. I define my models, which provide the state space X. I get a sensor mapping and a state transition function. So I start to have the pieces I need in order to make a filter over some information space. So I have to select an information space, and I want the filter to be practically computable over that space. I'm just putting all the pieces together now. And then I take my desired goal, which maybe is expressed in terms of states, right? Initially it's expressed in the state space. I have to try to convert it into an expression over the information space. In visibility-based pursuit evasion, the goal is to illuminate or see the evader. But I transform that into the information space saying, I want all of the shadow components to be clear. So that's the way of thinking for that. And then after I do that, I can compute a plan over the information space that achieves the goal in terms of the information space. It arrives in, I guess, capital G I called it before, which is a subset of the information space. So that's the idea, and I described it sequentially, but really you should consider all of this together, because if you make a poor choice in the beginning, there might not be a solution later. Or maybe I had sensors that are too powerful in the beginning, and I can still solve the problem, but there might have been a better way to do it. So in some sense, you have to consider all of this together if you want to make a very nice system or solution to solve some particular task. The only thing that's really fixed a priori here at the beginning is the task. I start with the task, and then I have to look at all of these issues. And maybe in my design, I might have to backtrack, go back up, and change the models to get a better solution. Or maybe one doesn't exist, and I have to go back up and improve it to get a better solution. Is that okay for the general idea? Does that make sense? That pulls together everything from the class now, right? All the different ideas. So now I now want to give you different ideas. I will start with talking about visibility, pursuit, evasion. Some I already have talked about it a bit, but I will remind you of it, and then I will go through some other examples of how this kind of mentality works. Okay, so under visibility-based pursuit, evasion, in fact, maybe I'll just barely get started on this, and then I will leave it for next time. Under visibility-based pursuit, evasion, mentioned this problem before, so maybe we have a single flashlight, maybe we have an omnidirectional visibility sensor. There's a pursuer, let's say, that moves in some way, maybe one or more, and the goal is to detect the evaders using detection sensors. These are very neat problems, right? You can say a solution for this, if you have omnidirectional visibility, in this environment is this one, for this environment it's that one, for this environment it's that one, and for this environment there is no solution. So it's very hard to look at the geometry of the problem and figure out whether or not there's a solution. It's very helpful to have a systematic algorithm for that. This one I think I drew on the board in the late afternoon session. Is very funny. If you want to clear this polygon, you have to visit the pair of feet here. You have to go up to the top every time for each pair of feet, because if there might be an evader hiding up there, I search this one, then I search this one, and then an evader could have snuck from here to there, so I better go up there. And then I search this one, and then an evader could have come from here and go up there. But I want to protect my work to the right. So it turns out you have to revisit the same place up there on the top. The number of times is linear in the pairs of feet. So there's all kinds of interesting questions here for this, the structures of these problems. What I want to point out is that for this problem, we did a combinatorial decomposition of the state space, of the information space. Well, both. So we do a combinatorial decomposition of the environment, which is part of the state space here for this problem. It's not all of it, but it's part of it. We do a cell decomposition based on exactly these things that we talked about before. Inflections and bitangents, which cause the appear-disappear, or splitting and merging of the shadow components. And then in the information space, we have this idea. So if I'm here, and we go in a loop, then the information state changes, but only when I go this far, this gets cleared, right? And so that means that we can divide the information space into these cells where there's no critical change in information, and then make an algorithm that searches by going from cell to cell. So we get systematic graph search. I already told you this filter that we have, where we keep track of 0 and 1 labels on all of the shadow components. And that's the basic idea for that. So we have this graph that we get from the cell decomposition, but we're also making an information state graph that gets systematically searched, right? So the algorithm goes and systematically searches, and as I said, in this case, we get perfect predictability in the information space, because all we need to do is describe a sequence of regions that needs to get visited. And it's a sequence that will systematically search, and it will cover, it will sufficiently search in the information space so that all labels are 0 at the end, and that solves the problem. So the plan in this case is just a sequence of regions that needs to be visited. Or you can have a particular path that's output that visits exactly those regions that's required. And so that's what we end up outputting for this. This one assumes, how should we feel guilty about this one? Based on what we've been talking about. So the way to feel guilty about this is that it required an exact representation of the environment, Maybe that's not needed. And it requires to know exactly where the pursuer is, at least to know exactly what sequence of cells it's visiting, right? Maybe you can get away with less. However, where it was a little bit clever is that you do not need to know where the evader is. So that's reasoned about as an information state. And then the task is expressed in terms of 0 or 1 labels on these shadow components where the evader might be. So that's where it was beginning to think in terms of reducing complexity and keeping track of information states. So that's why I presented this as a kind of example. And again, there were more complexity kinds of things we studied. Like you can show NP hardness of the problem because it's reduced from NP hardness of pursuit of evasion in graphs. And we also looked at the complexity of deciding whether or not K pursuers can search a polygon is NP hard. And this is some lower bound of how many pursuers are needed to search some polygons in the worst case. N is the number of edges and H is the number of holes in the polygon. And if you want to make an example that has no holes and needs log n pursuers, you can keep gluing polygons that have bent corridors in them. This one needs 1 pursuer, this needs 2 because somebody has to guard that. This needs 3 because somebody needs to guard that. And then you need to reuse a guard for these or pursuer for these, and so forth. You can keep doing this construction recursively, and you'll need logarithmically many pursuers in terms of the number of edges. So we have some number of results on these that many of you are aware of, but the criticism I want to make of our previous work is that they assume perfect mapping of the environment, perfect control, and perfect localization. So how can we go further from that? Like the gap navigation trees that I showed you did not assume that. We did some work that does pursuit evasion with gaps. And then it's weaker, but you can solve quite interesting problems that way. All right, so that's all for this time, and I will continue with maze searching for the next lecture. Are there any questions?